Hello, I'm Andre and welcome to a new episode. Today I will tell you about number bases like base 10, which we are using most probably because we have 10 fingers at our hands. So we're using base 10, and that means that we are using 10 characters for writing numbers, which are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And numbers like 10 use 1 and 0, 11 uses 1 and 1, and 584 uses 5, 8, and 4. And the same is for all the numbers. So we are using base 10, but I think the most popular base, the most famous base, except for base 10, is base 2, because computers use it, so you may recognize it as binary. And if we didn't knew any number base, the easiest one to learn would be base 2, and that's the reason why computers use it, and is the easiest to understand because it has only ones and zeros and it's not too complicated. So now but this would still make it confusing for humans to use it. It doesn't confuse computers, but us humans, yes, because we are too used to base 10, and we would have confusions like, for example, 5 in base 2 in binary is equal to 101, and we always would associate this more with 101 from base 10, which is a completely different value than 5. And for this reason it would make it confusing for us, but we still can understand it and use that base, but it would be confusing as a principal base. So now let's take a big number like 1024, and I choose this number for a special reason because it's 2 to the power of 10, and in 1024 in base 2 is exactly 1 0 0 0 0 0 0 0 0 0 0. So it has 10 zeros, which means that this is a pretty long number. So we can see that base 2 isn't very efficient in this case, because we can write an 11-digit number like this, an 11-digit number that's binary. Using base 10 we can write that using only 4 digits. So for that reason base 10 is better, but that doesn't mean that base 10 is the best. We can have other bases too. So a bigger base would be more efficient, but let me show you something about fractions. So the number of the divisors of the number you are using as a base is very important, because let's take for example our base 10. So base 10 has only 2 divisors, which are 2 and 5, and we won't in this video I won't count the divisors 1 and the number itself. Let's just look at the other devices. So it has only 2 devices, and that's not very much. We can do better than that. And let's so for that reason it's not a great idea to have a base that's a prime number, especially for big numbers, big prime numbers like 17, because 2 is a prime number too, but we have base 2, which is binary, and that's great. We use it for computers, and if it's not so efficient, it doesn't mean that's not efficient for computers. It's just not efficient and it's confusing for us humans, but for computers it's a great language. So what if let's see the numbers, and the smallest number that has a certain number of divisors. So let's start with 2. So 2 has no divisors except for 1 and itself, but if because we hadn't any numbers previously, that's the smallest number with no divisors. Then 3, it has no divisors, so it's not more special than 2. Then 4 has 1 divisor, so let's write that as green. Then 5 has no divisors, it's not more special. 6 has actually 2 divisors, So let's write that down. Then 7 has no divisors, 8 has 2 divisors but the same as 6, so it's not special. 9 has 1 divisor as 4. 10 has 2 divisors, the same as 6. 11 has no divisors, and then 12 comes in the equation. So 12 has actually as divisors 2, 3, and 4 and 6, so it has 4 divisors. So for this reason 12 is a better base. It has more divisors, and also it's more efficient because it's a bigger base than 10. So that's it. We could say that 6 is as good as 10 as a base, but it's not, because 10 is a bigger base and you can write numbers more efficiently. But 12 is more efficient and it has more divisors as well, so it's a better base. And why is better base if it has more divisors? Let's take fractions. If we have 1 over 1 in every base, that's 1. But let's take fractions like 1/2, which is 0.5. That's beautiful, but 1/3, I think you know this. If you type in a calculator 1 divided by 3, if you have 1/3, that's equal to 0.333333, and it never ends. And it's pretty confusing and hard to calculate with these numbers. Of course, you can write them as fractions and calculate with them like that, but it would be, I think it would be easier and you'd have more choice if it would be number nice like 0.5. And actually in other bases you can do that. So let me show you the examples that have these infinite repeating digits. So it's 1/3. We also have 1/6, which is 0.1666666, and so on. We have 1/7, which is 0. And this one's interesting, 0.14285.7, and then this whole string of numbers repeats. So again 14285.7, and so on. And actually this is very interesting because we have here at the denominator 7, and 14 is 2 times 7, 28 is 4 times 7, and 57 is pretty close, is 4 times 8 minus 1, plus 1. So 4 times 8 plus 1. And I think this is just an interesting fact. So this is in base 10, of course. Then we have 1/9, which is 0.1111, and so on. So these are the infinite repeating fractions, and of course there are infinitely many, but these are the fractions that have the denominator smaller than 10. Of course we could include 1/10, but that's a nice number, 0.1. But what if we would count in base 12? So actually in bigger bases we need to include other numbers too. So for example, let's take hexadecimal, which is base 16. So the characters for number, we have 16 characters, which are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and the new characters are A, B, C, D, E, F. That's an arbitrary option. Choose. So these are the first 6 letters of the English alphabet. And actually we in base 16, so A in base 16 is equal to 10, but it here is written as a single digit number. F in base 16 in hexadecimal is equal to 15, and actually 10 in base 16 is equal to 16. And I think that would be confusing because you associate 10 with 10 from base 10, which is not equal to 16. But let's move on to base 12. So in base 12, actually let's return to base 10. If we have 1/3 like this, so 1/3 in base 10 is equal to the base, which is 10, divided by the denominator, which is 3, and all this divided by the base, which is also 10. And notice that these operations are made in base 10, and that will be important later. So we have 10 divided by 3, which is 3.333, and so on, and this divided by 10, and that's 0.333, and that's as we saw earlier. But if we have 1/3 in base 12, that's equal to the base, so 12 divided by 3, and all that divided by the base, which is 12, and that's equal to by, and 12 divided by 3 is 4, divide that by 12, and that's equal to, so actually note that this would be 0.4 because we are dividing by 12, but all this in base 12. So actually dividing by 12 in base 12 is has the same effect as dividing by 10 in base 10. You just move the decimal point 1 unit to the left. So actually I think this is a little bit confusing, but I hope you understand. So it's actually 0.4. So it's not 0.333 and repeating at infinity, it's 0.4. So it's a nice number, and you have nice numbers also for 1/6 and 1/9. Of course, in every base you will have fractions that have infinite repeating decimals. In base 12, 1/7 is also something repeating at infinity, but it's much better because you have less of this. So there are bases with more fractions like this with repeating decimals, and there are bases with less of them. And actually well, from this point of view, prime bases are the worst because every fraction would have a result of these infinitely repeating digits. But base 12 I think is the best base, and it's also close to base 10. So from this point of view it would be a good alternative. So I hope you understand this video. I hope you enjoyed and learned something new. Don't forget to leave a like, to share and subscribe, and we see in my next video. Bye.